Why is it red? Isn't it green or blue when it's red? But it's fine. Alright, so we start. So if you recall last time we were talking about interval scheduling. The goal was to pick as many intervals that you can that don't intersect. And you can think of this as scheduling a shared resource that you don't want people to collide with, and there are other applications where this comes up. We had talked about greedy sort of methods, and different greedy methods would involve doing things that seemed reasonable to do, like the job starts the earliest, or sorting by increasing duration. We demolished two of those with cleverly chosen counterexamples. And we are currently battling with the third one to see whether we can either defeat it or it will defeat us. That's where things stand. And any thoughts on ways in which you can try to break the strategy of pick the job that is the earliest? And again, at some point, we'll have to stop thinking of counterexamples and start saying, okay, fine, maybe we should try to prove that this works, right? But the question is, are we at that point yet? Are we all given up on counterexamples? Do we have more? So again, the heuristic is pick the job that ends the earliest. So you take the jobs and sort them by the ending time, right? And then keep it, and then use that as zero, and then pick them as long as they don't collide. And we tried a couple of things that didn't seem to work, because remember, the goal is not to show that your answer is different from what you think the optimal solution is. Your goal is to show that your answer would have fewer number of choices. That's the thing, right? With a lot of these greedy methods, or any problem really, there are different optimal solutions, and we're trying to optimize the value, not the actual set of things itself. So, any thoughts, or should we try to just prove that it works? Okay, so we saw a previous example of how to prove that a greedy algorithm is correct. And if you recall, with greedy algorithms, that is the big challenge, proving that they're correct. Right? And the way we tried to argue was to say, well, the greedy algorithm produces a solution that has a certain property. Let's assume the optimal solution is different, which means it will not have that property. And then somehow show that you can make it look like it has the property without increasing its value. Right? So that you can make the optimal solution progressively look more and more like the greedy algorithm without changing its value. In the end, it becomes the greedy solution, but it has the same value, and therefore the greedy solution is optimal. That was the argument we had. So let's try to make the same argument here by trying to argue that any optimal solution kind of must have to do what this is doing. And again, with these things, one way to prove this is by induction. So let's say this is true for smaller sets of inputs, but now we have an input with n items in it, and now we have to reason about this. Okay. So let's start with the very first job, right? So let me create a page here. So the way we're going to try and prove this is by induction. So the goal is to show that, as always with the induction. So if there's one job, then greedy and opt will pick the same thing, and we're fine. So there's nothing to do. So that's the base case of the induction. So you first have an induction base case. So the inductive claim is that the opt solution, or rather, that the greedy solution is on, right? This is on inputs. This is the claim you want to prove, and we're going to prove it by induction. So the base case is n is equal to 1, and this is clearly true. There's only one thing to pick. Okay? And so the induction hypothesis is claim is true for sizes less than n. So let's look at an input of size n. Okay. So now we consider an input of size n. And then let the job ending earliest be the ith job. Let's say the job number I, it ends the earliest. So if we draw a picture, this is job I, it ends the earliest. Let's say its ending time is fi, finish I, right? And then everything else must end after that, by definition. It will be here, everything else in mind. Right? So this is what the greedy algorithm is going to pick. It's going to pick the job that ends the earliest. So now how should we construct the argument around what opt is doing? What should we say? If we go along the path that we did last time, what would we start by saying? So we have to say, something about opt, about the optimal solutions. What is the thing we must now need to assume about the optimal solution for this to become an interesting proof? In other words, where is the problem? Right, we're trying to prove that this algorithm always works. What could go wrong?
You have two jobs ending at the same time, potentially.
So let's assume that if two jobs end at the same time, we don't, we'll not tie break arbitrarily. In that case, we can handle. There was a hand up at the back there. Right in the back, yeah?
Yeah, we can assume that if it's not in our solution, then
that opt does not pick this one.
Yes.
So the job that opt picks is not this job.
Not
So why do we want to start with that? Because why do we want to start with that?
because we want to prove it. We have to pick the one that will end earliest.
Right, so by contradiction, let's assume we did not pick the one that ends earliest and opt to pick something else, right?
Yeah.
So that's what we're going to start with. So let's say, okay, assume, let me read these things. Okay. So assume that the job that ends the earliest in the optimal solution, right, is some j. Okay? So now if we draw the picture, so this was ours, right? And opt was something, we don't know where it was. And when you draw these pictures, it's helpful to draw them in the most, in the way that doesn't make any assumptions. We don't know where to start anywhere. We don't care where it started, right? But we know it ends after, it might look like this. It could also look like this, it could also look like this. But I don't, try to make it with as few assumptions as possible. That just helps so you don't fall into a trap in your routine. So we'll call this J, right? And we know that opt pick J did not pick I. Okay? We don't know if it could have picked I, but it didn't pick I, right, in this case. What is the next thing, if we remember from last time what we want to say? What is the kind of argument we want to make here? What do we want to do now to try and argue for the correctness of our greedy solution? So we have our solution, we have what opt might have done. What is the thing we want to say? You're going to say?
I believe that would prove that the solution that opt is picking has it has lesser number of classes than the solution I believe that part previously.
Right. So that's one that if that opt in fact went that route, it would do worse, which is not possible. Another way of saying this is that we could change opt into our greedy solution without increasing the cost, without decreasing the cost. Is that maximum? So my optimal solution is here. It's the best solution possible. My greedy solution is somewhere. I don't know where it is. And if I can make opt look a bit more like greedy and not reduce its cost, then I hope that eventually I can make it look completely like greedy and not reduce the cost, and then greedy is therefore opt. Right, so it's one of those things where either opt goes towards greedy or greedy goes towards opt. Yeah.
What do we mean by reducing the cost?
Dropping, as you said, having fewer number of items. Sorry, cost is the wrong term here because I want to maximize. I want to pick as many items as possible. A bad thing would be if I had to drop intervals, if I had to reduce the number of intervals in my set. I don't want to do that. Right? I want to be able to say, look, I can make this look like greedy without changing the number of intervals in my solution. Okay? Yeah? So how would you argue that here? Well, here's the thing. We know that in the optimal solution, the intervals do not intersect. That's just a feasibility constraint. None of the intervals can intersect. So can we say something about where all the intervals in the optimal solution must start? We don't know much about opt, but we do know that all the other elements of the optimal solution must start here. Right? Because opt is going to give you an actual solution where things don't intersect. Correct? Okay. Yes?
It's not exactly from that point, right? You can start after a bit of that.
Yes, but they do not start before that.
Okay, okay.
So in other words, if this is fj, right? For all indices in opt, right, where k is not equal to j, we know that sk, and we'll assume that they're not perfectly aligned, or is greater than equal to f of j. Right, the start time of that item k must be greater than or equal to the end time of j. Right. So I'm not saying it's exactly that. I'm just saying it's greater than or equal. Right? So we know this is true, but we also know by construction that fj yes, because by definition greedy picked the one that ended the earliest and opt did not pick it, so opt's ending time, the one that opt picked, its ending time must be more than the one that greedy picked. Right? Yes, yes.
Would it be strictly more than?
Sorry?
Wouldn't it be strictly more than?
Yeah, I'm being a little sloppy with numbers.
Okay.
Right, but you're right that it. So if we assume that no two intervals have the exact, so there are two ways to deal with this. One way is to say that no two intervals have the same exact ending point or starting point, and you can always do that by stirring them a little. Or you can say that my notion of greater than or equal to is a tuple, where one component is the actual finish time and the other component is some kind of lexicographic identifier. So you can always reorder two things. So this allows me to sort of say that okay, this that they're distinct. Okay, so for now, let's just use a simple way out. Okay. So if we put both of these two things together, we can say that again. Because if Sk is greater than or equal to Fj and Fj is more than Fi, then Sk is greater than Fi. Which means that the new solution, so we now look at the solution, consider S is equal to I union the K belonging to opt such that K is not equal to J. S is feasible. S is a valid solution. All I have done is basically swap out J from optimal and put I back in. Right? This is now feasible. But now this new solution, which has the same value as opt, does in fact pick the item that the greedy would have picked first. And the crux of the argument here is that because we look for the one that ended the earliest, everything else is cleared out after that. That's why we could even make this argument. Okay? Alright, so now what? So it seems like we made some progress. So we start off by saying, look, opt did not even pick the one that, the first one, the one that first. We say, okay, look, we can pick it. It doesn't affect us. We can still be opt. So what do you think we need to do next? When you feel like you need to go again and again and again, remember how we were trying to prove this. How were we trying to prove this? Yes?
I mean, with the assumption that the classes that appeared before J or in our solution before I are equal.
Sorry, say it again.
So we're talking in terms of the number of classes that I can attend, right?
Yes.
So do we assume that the classes that appeared before J
In which solution?
in optimal solution?
Are there any solutions appearing before J in the optimal solution? First of all, I don't know what appearing before means. What does appearing before mean in your
I
language?
mean, so I'm a little confused about like we can swap. We are trying to swap out J with I, right?
Yeah.
I don't know. It will be clear when
No. It should be clear now. So what is the question? So let's stop it.
I mean, how can we conveniently swap I with J?
Okay, what I'm saying is this. And this I think maybe I understand where but I need to be more clear. So I think you're confused about what happens here.
She's confused if it's the first inverter.
Right. Is there stuff here? So here's my question for you. What did I say about J? Assume that J is the job that ends the earliest in opt. Right? Now there might be jobs that start before J, but they end after J. But could I have picked those? Would opt have picked them? No, because the opt picked, this is the one that ends the earliest. Opt could not have picked anything that started before J, because such a job has to end after J, which means it intersects with J, which means it's not feasible. So if we look at the job in J that ends the earliest, we are guaranteed that every other job in opt, every other job in opt must start after that. That's why I wrote this statement. It cannot be that there's anything before, because then that would have to intersect. The only way that would not intersect was if it started and ended before. But that's not possible, because this is the one that ends the earliest. Right?
Yeah.
You see how all these threads are hooking up together? The reason I can make this claim is because this is the one that ended the earliest in opt. I couldn't have made this claim otherwise. So the truth of this statement is basically the truth of what you're asking, right? That there is nothing else. Everything has to start, in fact, after this one ends. Okay?
Yeah.
Otherwise, I can't say any of these things. Right? And so therefore, the reason, because all of these must start after the first one ends, I can now swap them out. Because now we know everything else in opt is here. Swapping out those two is not going to affect the feasibility of the solution. Does that make sense?
Yeah.
It's kind of, sort of, yeah.
Where are we using the induction to less than n right now?
I am waiting for someone to use it. We haven't used it yet. We have not. And I didn't say the proof is complete either. But I kind of basically said, okay, what next? Maybe that's what next needs to happen. Someone needs to rescue us with the induction proof. Where would that go from? Yeah.
Isn't the sentence like presume that the job ending earliest in opt Bj is a bit confusing? Shouldn't we rather say that the job that opt picked for the optimal solution is J? Because it's the same problem as us, right?
Yeah.
So it's the same problem.
To me, this sounds like the same sentence, but maybe you're hearing something different.
Okay.
Yeah.
What you are saying.
Let me say it again. What I'm saying is look at opt. Take the job and opt that ended the earliest. That's index J from my input set. It's the same input, you're right? Yeah. That's all I'm saying. I'm not saying anything more than that, but yeah, I think you've got the same idea.
Yeah, I got the same idea.
Yeah. The wording is confusing. So you're saying I shouldn't say assume, just say, okay, let's look at the job that ends first, that's called a J. We're not called a J, it is J, basically.
Yeah, I'm saying like, since it's the same problem instance,
Yeah.
the earliest job that is ending is I, we already said that.
No, for greedy.
That is not greedy, but
Yeah.
it's the same problem instance and
So-
we are looking the same.
No, we're not looking at the job that ends the earliest in the input. We're looking at the job that ends the earliest in the solution.
Okay.
These are two different things. Right? There could be many jobs that end right here, but greedy didn't pick them and opt didn't pick them for whatever reason. I'm not talking about those. I'm talking about in the solution. That's why these two can't be the same, or may not be the same. That actually is a point I want to make sure it's clear. We're talking about the solutions. Okay.
So J is from the solution and I is from
J is from the optimal solution. I is from the greedy solution. So we're saying the greedy solution happened to pick item number I to be the first one. So I have my inputs, right? 1 through n. Right? The greedy solution does and okay. It said, okay, I is the one that ends earliest. In fact, I is the one that ends earliest in all the input because that's how greedy works. And it picked that and said, okay, this is the first one. Opt said, nah, you're a moron, so I'm going to pick J. So it picks J, which is different. From the same input, but the solutions picking are different. Right? Is that clear? Okay, good. I'm glad you asked these questions because these are important points to clarify. That the optimal solution, J happens to be the first one, in the greedy solution, and in the input, I happens to be the first one, yes.
Yeah, so even now we collect that we have to pick I is the earliest in greedy, but even if we don't pick I, we still have the optimal solution because the optimal solution included J equal value with the picking I. So
I'm not sure what your point is.
to take J out of the optimal solution,
Yeah.
and replace it by I.
That's what you're arguing is possible. Yeah.
Yeah, that's possible, but it doesn't make the solution better.
I didn't say it makes it better. I said it doesn't make it worse.
But
No, this is an extremely important point. I did not say it makes it better. I said it doesn't make it worse.
Sure.
Okay.
Yes, sure. Then even so means that we don't need to pick I. It's still I have the good solution. It doesn't make sense. You can
Let me
pick
finish.
I,
Let me finish the proof. Let me finish the proof. Okay.
Okay.
Okay. Then we'll see. This is the weird, I think, somewhat counterintuitive things about greedy algorithm proofs, but which I think you're hitting on right now. But let me finish it, and then we'll do this. Okay. I'm guessing that many others share this sort of feeling about what the heck is going on here. Is that sort of a similar sentiment? Okay. Good. So to complete the proof, I think Vivek has volunteered to do this for us. This was your idea. Because you're the one who complained that we had this nice little induction thing lying on that we forgot to use. Generally speaking, if you have assumptions in a proof and you have to do something, that's the time to pick it up. So this is the thing, right? If you see a gun in Act 1 of a play, by Act 3 someone needs to shoot the gun. So I start with induction. How do I compute this proof with induction? How would you do it? Remember what I said. I started off with an optimal solution that did not agree with greedy at all. I changed it to this new solution which now agrees with greedy on the first element. How do we use this to complete the induction?
Change the position to center.
Second, to the second one.
Center, anywhere.
Center.
I'm having some elements before.
No, sorry. I'm only allowed to use induction arguments. Put this in the language of the induction argument. What does the induction argument typically look like? An induction argument says, assume things are true for small values.
Yes.
I have to worry about big values. I do something for this big value and reduce the problem to reasoning about a smaller size input where I can apply the induction claim.
Okay.
That's all you're allowed to do. So one of the things that I will say, and as I look through your homeworks, and this will probably come up, is that there is a tendency to try and sort of say things that would seem like they make sense in a proof. I want you to resist that urge. Proofs are very structured objects, right? If you are doing a proof by induction, it better be a proof by induction. You don't bring a knife to a gunfight, so to speak, I don't know why I use all these violent metaphors now, but anyway. So, but if you are going to say, I want to prove by induction, you don't go off into a long digression about other fun things you might. That's great, it's all good. And that's a good chat to have over coffee or over something else or whatever. But in the proof, no. I've said I'm proving this by induction. I will only use induction. Do not try. And this is not for my benefit. Well, it kind of is. But it's mostly for your benefit. You will get distracted. And you will start wandering around. You will think you have said a bunch of things together that somehow slurp up into an argument, and they will not be, and you will not get points for it, because I will complain about them very loudly, and then you will complain about me to your friends. So to avoid all that complaining, make sure your arguments one step follows from the next. We had induction argument. The induction argument, we know the basic structure. Prove it's true for the base case. Assume it's true for small values. Reason about higher values by using the lower values as something you can rely on. We did the base case. We made the induction hypothesis that it's true for small values of n. Now we have n. We did something here. We got some new input. Somehow this needs to help us. We need to use the induction claim now. Somehow we need to come up with some smaller set where we can apply the induction hypothesis. Where is that smaller set? Remember what we've done. We've taken out one of the differences between greedy and opt, right? That IJ difference. We've now constructed a new solution that is also optimal, but agrees with greedy on the first element, okay? Now if you look at what's left, both greedy and opt are given the same set of things to organize. Because the greedy solution, the greedy choice was the black one. The optimal choice was the red one. Anything you picked for the optimal, you could also pick with the greedy choice. There is nothing limiting you from using all the rest of the optimal possible feasible answers for the new case where you've replaced J by N. Your set of feasible intervals has not changed. If anything, it's gotten a little bigger. Which means that if you now apply the induction hypothesis on what's left, we have assumed that on a set of size less than n, the greedy solution is in fact optimal. If we now look at the set consisting of everything that's left, we know the greedy solution is optimal on this. We know that both opt and greedy have this one element. Therefore, by induction, we are also optimal on this. No other discursions into interesting properties of the sets. So again, we know that the algorithm works on inputs of size n minus 1 or less. All we have to do is somehow get down to an input of size n minus 1 or less. And that's what we've done here. Because we eliminated I and j. We swapped I for j. And that is how the induction proof works here. That we've, and another way to think about it, so any good proof usually has like 5 or 6 different ways to think about how it's working. And sometimes it takes a while to see them. But another way to think about this is that, and this goes back to your point, right? All we did was change opt to look a little bit more like greedy without reducing the cost. We didn't make it better, but we didn't make it worse. Now we do this one more time. We change it to look a little bit more like greedy, and again without reducing the cost. And again, and again, and again. Eventually, we have a solution that looks just like the greedy solution and does not have any reduced cost. But we just said this is optimal. Therefore, optimal is greedy. I don't know if you know about this old sort of metaphysical philosophy thought experiment. Have you heard about this? So you take a ship, you build a ship in a brickyard, right? And you build it with this wood from this tree. And then one day the piece of wood breaks and you replace it by another piece of wood. Another piece of wood breaks and you replace another piece of wood. Eventually, you have a brand new ship. But at what point was a ship the old ship, and what point was it the new ship? So this is one of those things that people, the Greek philosophers, sort of talked about, and it relates to notions of identity. And you replace your arm by a bionic arm, another one. At what point do you stop being human, right? At what point does the solution stop being optimal and start being greedy? There's no point along the way. You're just continually changing it bit by bit without actually changing its cost, and suddenly it becomes the solution that you produce from your algorithm. And because you did this without ever reducing cost, the solution you produced must also be optimal. That's the reasoning. Okay? Because remember, all we're doing is looking at the size of the solution. We are saying, we basically have proven that the greedy solution size equals the optimal solution size. Therefore, it's optimal. It may not look exactly like it, but we don't care. There are many, many possible optimal solutions. If you remember a long time ago, how long ago? Many, many slides ago, I drew a picture out here, right? And I said that the way you prove these things is that you say, there's a bunch of optimal solutions and the greedy is one of them. And what we're saying is here, we start from some other optimal solution, we can move around in the space till we get to greedy without leaving the space of optimal solution, because we never reduce cost. And that's what this proof is. So greedy algorithms work essentially like this. There are usually two ways, but they're very equivalent. One way is to say that at every step of the process, the greedy algorithm is always at least as good as the optimal solution. And in some sense, that's what we're doing in interval scheduling. We're saying that no matter what you do, the greedy solution, right, is further behind what the optimal solution does. So you can never do worse than optimal, because you have more possible intervals to choose from. If you chose the one that ended first versus something else, there's this little window where greedy could have chosen something that opt did choose. So you can't do worse than it. The other way to think about this is that the optimal solution gradually mutates into the greedy solution without changing its cost. And then this works. Yeah.
So the idea of the greedy solution is one of the optimal solutions, not unique.
That's right. I'm not saying anything about uniqueness at all. And that's very important, because that, if you try to prove uniqueness, you'll almost never be able to prove it. That's not the goal of a greedy solution. To be, and in fact, in these cases, you often won't have unique solutions. That's why the opt is defined by the size, not by the actual solution itself. There are many possible equivalent class schedules that are equally valuable. And in fact, one of the assignment questions is, what happens if they're not equally valuable? So, you have to look at it, yes. Yes?
So we made the induction hypothesis that the
The
claim
greedy
is
solution,
true
the
for
greedy
any size
solution is
cluster.
complex, size estimate, yes.
Okay, so that's our hypothesis.
Right.
And I understand that we say that the greedy and the optimal are true or are the same for all elements beyond, all intervals beyond that first interval.
Which is of size n minus 1.
Right. So does that alone prove the hypothesis?
Right. That proves it, yes. And here's how to prove it. So what we're saying is this, okay. So let's call this, so let's define, so let's do this. So let I equal to all the elements, all the intervals, such that I is not equal, or not I, all the intervals, actually, that I be the set of all intervals minus I, because we picked I. Okay. Now this set has size n minus 1. Okay. Now we know that by the induction hypothesis, the greedy solution on I is equal to the optimal solution on I. This we know. This is our claim. Okay. We also know that that the set I is okay. Let I opt equal to set of all intervals minus j, which was the one opted. Right? We know that I contains I opt, just because the greedy, because j, I ends earlier than j. Okay. Therefore, given that we can swap I and j, the size of the solution, so the optimal, so then we said that the greedy solution on all inputs, should I give a name for the whole input, is equal to 1 plus greedy I which is equal to 1 plus greedy opt, 1 plus opt by the induction claim, right? Which is no worse, so I'm going to say greater than equal to, which is no worse than 1 plus opt on I opt, right? Which is equal to opt. Okay, let me walk through this. So what I'm saying is this. The greedy solution on all inputs, the size of the greedy solution, is 1 plus the greedy solution on what's left. That's just basic, to take one out, put one in. Because of the induction hypothesis, it's the same as 1 plus the optimal solution on what's left. Because I contains I opt, right? Because there are more possible choices for things to pick after you picked I versus after you picked J, because I ended earlier. Clearly, this is a greater than equal to. If I gave you more things, you should be able to do better. So this is clearly true. But this is opt. So the greedy solution is greater than equal to opt, which is all we need to prove. Of course, it won't be greater, but that basically makes it equal to. This is how the induction hypothesis is being used here. Does that answer your question?
Yes.
Right? So this is exactly how you reason it. Or this is one of the many ways in which you can reason, since proofs are not unique either. But this is how you connect the induction claim, the induction hypothesis, and the base case all together. And that's why I said, it's one thing to think about where the correctness of the argument is coming from. And that's what we were doing with these arguments. But eventually you have to stop and say, okay, I need to write a proof. That's what the proof is. So often when you read a proof in a paper, they've done all that work and they've written a proof for it, and it's often your job to deconstruct back from what's written to what the idea was. And the same thing here. All the stuff I wrote out to you, that's the idea. This is the proof. Along with the fact that that this holds, right? This fact here is all we needed. That the greedy solution gives you more feasible space in the optimal solution. Okay. Any questions? Before I move on to the next greedy sort of instance you want to look at? Okay, the last step says 1 plus opt on what's left on I opt is opt. Why? Because what is I opt? I opt is a set of all intervals minus j. J was the first element of opt. So question? This might take a while to sink in, so I would suggest you go back and read this again. Okay. Let's look at another problem. The more we look at it, the more we'll hopefully get comfortable with this. Next one we'll look at is this one. So we have a graph, it's not a directed graph. We'll get to the usual stuff. And what we want to find is this thing called a spanning tree. So first of all, each of those words has an important meaning there. Let's take them backwards. We want to find a tree. What's a tree? A tree is a graph that has no cycles. Right? It branches out, there's no. Okay. What's a spanning tree? A spanning tree is a tree that takes some of the edges of this graph but touches every vertex. Think of it like a communication network where everything is connected. But it's a tree. So it's the smallest connection. So a tree is the smallest, is the smallest connected, graph you can build on certain nodes, right? So a spanning tree is a tree that spans all the vertices. It looks like this. It's a tree, there are no loops. It's a spanning tree because every vertex is in that set. It's touched by some edge of that tree. Right? If I didn't have this edge, for example, this vertex would not be touched by anything in the tree. This would no longer be spanning. It would still be a tree, but it won't be spanning. Okay? Now there are many ways to construct a minimum spanning tree. By the way, how many do you know how many edges a spanning tree must have for a graph of n vertices and m edges? There's only one answer. Yeah.
Step minus 1.
So every tree on n vertices, it's connected. It's not a forest, right? Has n minus 1 edges in it, right? So if you're thinking, okay, I want to find a minimum span tree, it doesn't make any sense because they all have n minus 1 edges in them. All these edges have weights. Some edges are more important than others. You can think of this as you're trying to build a communication network out, which is a tree, and some edges are longer, you need more pipe on them. Right? So every edge has a weight here. This. Okay. And what we want now, so we're going to put a weight here. So this is like 10, 1, 2, 3, 7, 6. I don't care, whatever they are. I'm not going to make any assumptions. They're all positive. That's whatever. 9, 1, I don't know if that makes sense. We'll see. And now I can add up the weights of all the edges in my tree. So this would be 10 plus 7 plus 2 plus 1 plus 5 plus 7 plus 2. And this is like 34. So the cost of this tree is 34. Now clearly I could have taken a different edge, right? So for example, what I could have done is remove that edge 2. So now, I expect to get both these trees and I can't get both, so okay, I don't want to do that. But let me convince you that this tree is spanning also, right? Every vertex is touched by one of those red edges. But the cost of this now is 1 less. Not add, let me just check, right? The cost of this tree is now 33. I have achieved a tree of slightly smaller cost. So this gets us to the third one in the name of the problem. Find a spanning tree that has minimum cost. The cheapest possible tree you can pick out of these things. Okay? Problem clear? Right. It's a very core, one of the most fundamental problems in graph algorithms, finding a minimum spanning tree. It's a very important problem. A lot of problems use this as a subroutine. So first you find a tree in the graph and use the tree to do some other decomposition or whatever, and often you want to find a minimum cost tree, and it has to be spanning because you don't want to forget certain vertices, so you want to find a minimum spanning tree. So it's like sorting almost, it's a very core fundamental problem. And so the question is, how do we compute this minimum spanning tree? So I hope the question now is clear, right? What we want to do. So the input again is a set of vertices, edges, and weights on edges. So my input to my problem is I'm given a graph G, which consists of vertices, edges, and a weight function, where the weight function is from a set of edges to the positive rails, using the positive images. This is my input, and my goal is to find the minimum spanning tree. There are many, many different algorithms for this problem. So there are many, many different possible, and they're all greedy, so you can come up with different greedy solutions. But let's again think, if we have to design from scratch, what would a greedy strategy look like? Yeah?
Start at the vertex.
Start with vertex.
Pick the minimum edge of that vertex.
So take a start a vertex, we have to cover that vertex somehow because it's a spanning tree. And we want to be greedy, so we want to connect it as cheaply as possible. So we connect it via the cheapest edge coming out of it. Okay, so now we have to, now what do we do?
I guess now pick the cheapest edge that doesn't create a cycle.
Coming out of?
The newly discovered edge, I guess.
The newly discovered one?
Yeah, so you go to the vertex that edge connects with that receipt.
Okay. So I'm going to write down strategy 1. And you know what your game is going to be now. What's the game?
Break it.
Break it.
Can we patent this or make it a TV show?
Sorry?
Like make it a TV show so Jeopardy was called Break It.
You know I would watch the show.
Okay.
And I don't know how many other people would. It'll be very popular. Extremely popular show among a very small number of people. Okay. So strategy 1. Pick a vertex, pick cheapest edge out of it, move to endpoint. I think this is, I'm just rephrasing what you said. Endpoint of edge, repeat. Is an accurate rendition of what you said?
Yeah, and then pick an edge that doesn't create a cycle.
Yeah, okay, as long as, well, okay. Repeat without creating cycle. Good. And once again, I just want to highlight the greedy stuff.
Okay.
Yes. Wait, this is done. As far as I can tell, this is done.
What's that?
You want to add more to the algorithm?
Oh yeah,
The rule is, here's the rule in this game show that we're designing.
Yeah.
You have to specify the algorithm, you're not allowed to change it. Because when people start breaking it, you're not allowed to change it.
Okay.
Otherwise it'll become this whack-a-mole problem. So, tell me you're done.
And then if it does create a cycle for all the edges or all the vertices that are not connected yet, go back to a vertice where one can be.
Oh, now you're adding some extra catch. Okay, so.
Well, I wasn't. Yeah.
Okay, sorry, go ahead. So if not possible.
Yeah, if you can't add one, but all the vertices are not connected.
Yeah.
Go back to a vertex which one can.
Which one?
The nearest one. I guess.
What's the nearest?
The suit. I guess.
It's an algorithm. You gotta be precise. Yes.
What's that?
The lowest weight for the unconnected node.
Or the so you're backtracking, right? The
Yeah.
first backtrack is.
Oh, the one you previously considered.
Yeah.
Okay.
Yeah.
Okay, I'll say backtrack. I think we can agree with backtrack means. That was different to what you were suggesting.
Yes.
But that could be strategy too, once we crash and burn his algorithm. Okay, let's break it. If you can. Yes.
Okay, so whatever vertex you started at,
So I'm going to start at vertex, yeah.
sure. So you're picking the lowest cost one, right?
Edge coming out of it, yes.
So let's say that there's 3 nodes connected to it, and 2 of them have like cost 2, and the other one has.
I'm just
cost.
putting numbers to the vertex so we can
Okay.
talk about it. Yeah.
Okay, so like give edge weight of 2 to a couple of them.
To a couple of them, not all of them.
No. And then give 1 to the other one. So we know where we're going, right? So then we go to 3.
Okay.
Now add a couple nodes to 3. And do like 10 and 12.
I like where you're going.
And then connect the end of one of those to one of the previous, like 2 or 4.
I mean, with a new edge or just move that vertex so it's like.
Add a node to the end of both of those.
So let me label them. Okay, this is 5 and 6. Okay, what do you want to know? Add an edge between 5 and 2.
Sure, yeah.
And what weight does it have?
45.
45. That's exactly how you should do it. Don't be afraid to pick the huge numbers. Okay, is that enough? Okay, you're claiming his method will break.
Yeah, because you should.
Okay, let's run it. Let's run it now. I got the input. Okay, so we start off at 1, because you didn't tell us where to pick, so we're going to start at 1. We're going to choose the worst possible starting point. I'm going to pick good from 1 to 3. Then we're going to go from 3 to 6.
Change the number.
Hey, no, same rule applies to you. Sorry. You can't change the counter example. That's not fair either. No. So we go from 1 to 3. Go from 3 to 6. Now we are stuck. So we backtrack to 3. And we pick one more from 3. We go back to 1 now. No, you're just nodding. What do we do?
Oh. Oh no. So you go back to 3, pick 5, and you go back to 1.
So I go back to 3 and pick 5.
Yeah.
And then from 5 I go to 2.
Yep.
But this is still not spanning because I don't have a way to pick 4. So I can't make a cycle here, so I go back. Okay, so the solution here looks like this.
It was okay. I thought it was going to be bad.
This is why I said, don't jump in. Try it out first. Okay, it's a tree. It's a spanning tree. Its cost is, well, large, clearly. Could we have done better? I mean, this is not a counter example unless you could have done better.
Yeah.
What could you have done better?
Pick 2 instead of 45.
And then your cost would be? Yeah, you would pick the first.
Yeah.
Okay. Let us bring out the ceremonial red pen. Oh. There's certain catharsis in doing that. Like, okay, that idea is gone. We're not ever think about it again. What's the next one? No, someone else. Yes. Actually, well, let me get to the back then, because you don't have a chance to speak about it.
So it's kind of the same as the first one, except you just pick the edge with the smallest weight.
How is that different from the first one?
You're not starting with a specific vertex, you're just picking the edges with the least weight.
So your first step is to pick what? Pick the edge with the cheapest weight.
Yeah, with the lowest weight.
Lowest weight, and then?
And then you
So I pick that edge.
And then you pick the next one with the lowest weight, as long as it doesn't create a cycle.
But does it have to be connected to these, or no, you don't care?
No.
You don't care, you just pick an edge, this thing.
Yeah, as long
okay.
as...
So let me write down strategy. We're going to be on 10 minutes, so let me just write this down. So strategy 2 is pick edge with cheapest weight and repeat as long, and repeat, well, let me not, so not as long. Skipping edges that form a cycle.
And repeat until all the vertices are touching.
Until all vertices are covered. Okay, this is an algorithm. It's, as far as I can tell, well specified, so I can implement it. And we have, let's see, the last minute. Do the thing. So again, I identified here where the greedy step is. The first thing you should do, since you have built up this nice collection of counterexamples, hopefully in this process, run the new procedure on the old counterexample. You have one, might as well try it. What did it do in this case? We'll assume tiebreakers are resolved arbitrarily. So let's pick our first edge to be 1 and 4, because that seems like it would make the algorithm work harder, and we want to do that. So use a different color.
Is
So
it 1 and 3?
1 and 3. No, I'm saying I can pick either. So I'm just going to make my life harder and pick 1 and 4. Right?
No, it's 1, right? The weight of 1 and 3 is 1. So.
Oh, sorry, my mistake. Of course you have to pick 1 and 3. Okay, I think that one. Sorry. Okay, what are the next? By the rule, the next one I should pick is either 1, 4 or 1, 2. Right? So let's pick 1, 4. By rule, the next one I should pick is 1, 2. By rule, the next one I should pick is 3, 6. Yes. And then the next one I should pick is 3, 5. Hey, it worked. Well, clearly this is correct. Is it? No, it wasn't that counterexample. That doesn't mean there isn't a more clever counterexample to break it. But it's always good to check these things. Since you have counterexamples lying around anyway, you might as well run them and see. Think of it like unit testing. Okay, we're out of time for today. We will pick this up on Monday, but in the meantime, think about how you would break this. And one thing I want to say is that it will take you like probably 10 seconds, or as long as it takes you minutes time for you to find the answer to this problem. I'm pretty sure you can do this, and I'm not worried about that. If you do that though, you will get the answer. What you won't get is the process of learning how to find it. And that's what this class is all about, right? So the goal is not to get the answer to this question. The goal is to learn how you get to the answer to this question. So I know you can look for the answer, I know you'll find it, and you will get the right answer, but you will not learn that process. So try and play with this without looking up, just see what happens. And if you are unable to find a counterexample, then see if you can apply our principle of induction and changing, and try and see if you can come up with the proof yourself. You'll be surprised how many ideas you've already had that are in fact correct answers to problems we've seen in class. So it's not that you can't come up with the ideas yourself. You just have to learn how to think about them more rigorously. So I'll leave that. Okay.